Welcome to today's webinar, Best Practices for Running MongoDB. Our presenter today is Rahul Bairita. Rahul is a Partner Solutions Architect at Amazon Web Services. He helps AWS technology partners with architecture and integration of data and analytics applications for the cloud. Prior to joining AWS, Rahul spent 10 years gaining experience in architecting data and information processing systems at companies like PayPal and Cognizant. Today with us, we also have Rick Houlihan, Principal Solutions Architect, Jorge Lopez, Senior Solutions Marketing Manager for Big Data, and Jason Ma and Mrinal Sarkar from MongoDB as our webinar moderators. They will be engaging with you and answering your questions throughout the presentation while our presenter presents. Rahul, welcome. The floor is now yours.
Thank you. Welcome everybody to the webinar today. And today we're going to talk about MongoDB. Based on the two poll questions you saw earlier, you might have noticed the questions were asking how familiar are you with MongoDB and AWS. We saw that around 30% of people on average indicated that they are not familiar with MongoDB and AWS. So to cater to those people, we also will cover some basic areas in terms of MongoDB and AWS. But around 60% of people mentioned that they are somewhat familiar, and we'll try to cover the features which cater to those audiences too. That will be our basic agenda for the webinar today. So we're going to talk about MongoDB, do a basic introduction of MongoDB and AWS in the context of MongoDB, and then in the end, we're going to try to cover the best practices for running MongoDB on AWS in terms of making it highly available, fault tolerant, and other such practices which are aligned for cloud deployments. So with that, first, let's start talking about MongoDB basics. As you might know, that MongoDB is a system which stores data as documents called binary JSONs or BSONs. The binary JSON encoding scheme basically extends the JSON documents and add some capabilities to store data types such as integers, longs, and dates. But you can think of the BSON documents which are having fields, and each field contains a value of a specific data type, which could be arrays, which could be subdocuments, or even a binary data itself. It may be helpful to think of documents which are roughly equivalent to rows in a database table. Each row in a database table will correspond to a document, and within that there are columns which are represented as fields within MongoDB, and a collection of documents which basically corresponds to a table overall in a relational database. As you might see on the screen, it tells you that a representation of a simple application and how it might be represented as two tables in a database versus as a single collection or a single document in MongoDB. You can see that having representing data in this way provides you more natural representation. So you don't have to do a object relational model or a model which translates relational data sets into objects for use into programming interfaces. And this helps you with developer being more productive. Not only that, it kind of reduces the needs for joins to multiple disparate data sets, because a single connection holds all the values you need to answer a particular question or implement a particular use case for that matter. So, and collections are dynamic in the sense they are not defined schema. So they allow you to kind of evolve the data model as the business changes. So you can rapidly iterate over your business or your needs as the data set evolves. This is the basic data model of MongoDB, which is a NoSQL database. But on top of a dynamic schema, MongoDB also allows you or have features which allows you to interact with data in a more productive way or a more faster iterative way. For example, you can do a rich queries via find operator in MongoDB to say that, let's say, do a find on everybody's whose name is Paul, which will give you all the cars owned by Paul. You can apply such actions like sort to say that data which is done between 1970 and 1980s. You can do geospatial queries to say that give me data points which are within a circle of a given points. For example, you can say that find all the car owners within 5 kilometers of Trafalgar Square. Not only that, you can do a full text searches. For example, you can say that cars text.find where car notes says that it has leather seats. And these ways, it allows you not to bring the entire data back into your application, but these queries does the processing on the MongoDB server side. So your application could be much more thinner in terms of functionality, and it only has to deal with the functionality instead of trying to do these things from a data management perspective. Not only that, MongoDB has an aggregation pipeline, which allows you to process data through multiple stages and at the end get a result set based on that. So for example, you can say that not only find all the cars which are owned by Paul, but give me the value of that, of the total value of the cars which are owned by Paul. And at the end of it, it also has a map and reduce paradigm in which you basically take a set of documents, map them into a values, and finally do a aggregation over those values to say what is the simplest application coming out of that. If you're familiar with Hadoop, this is the same concept, but applied to MongoDB as a documents or as a collections. Such features allows you to interact such features allows your applications to interact with MongoDB in a much more faster and iterative way. Having covered the basics of MongoDB, we're going to talk about MongoDB 3.2 release, which just got released last month, and talk about the new features which were made as part of release 3.2. The first new features we're going to talk about is the storage engines. Starting with MongoDB 3.0, MongoDB introduced a new storage engine API, which enabled the concept of pluggable storage. Essentially, it means is that you can run the MongoDB as a database, but you can replace the underlying storage with a variety of options. The default, which was default post pre 3.0, was something called memory map, and that memory mapped storage layer allowed you to take your files sitting on your disk or on your drives and put them into an operating system virtual cache. So MongoDB could operate or could interact with those files while they're in memory. Starting with 3.0, it added a new interface called Wired Tiger, which allowed you to basically use the underlying storage in a much more effective way. And not only that, it actually brought document level concurrency with Wired Tiger. Starting with 3.2, Wired Tiger is now the default storage engine, which means that if you just go and install MongoDB and run a 3.2, it will by default use Wired Tiger storage engine. There are two more additional engines introduced in 3.2, which is an in-memory engine. In the in-memory engine, all the data basically resides in memory and is never written back to disk or to drives, which is the case with the memory mapped or the Wired Tiger engines. And there is the encrypted engine, which basically allows MongoDB to encrypt all the data at rest. It is an API on top of the Wired Tiger engine. Both of these storage engines required you a MongoDB Enterprise Advanced subscription, which means that it's not the open source version of MongoDB, but you need to get a licenses to run these storage engines with MongoDB 3.2. While having a dynamic schema is great, it brings you a lot of flexibility, but there's also need for data governance, for example, which you can enforce in a relational database using concepts like foreign keys, primary keys, uniqueness, and other things. You can think of data governance or document validation as a feature introduced in 3.2, similar to those constructs, in which you can enforce a validation on a collection before it gets inserted or written or updated back into a database or into MongoDB. It allows you to enforce data quality across multiple team scenarios where multiple applications or multiple teams are writing data into a single applications. And you are using the familiar constructs of MongoDB expressions per se in terms of validating that document. For example, you can say in the example on the screen that db.run command, and there's a collection mod operator, which is basically adding the validator to say that year of birth is less than or equal to 1994, or the phone number and email are of type string. And this allows you to basically enforce a data governance while still adhering to the basic principle of dynamic schemas into there. The validation is optional. It could be as simple as single field or compound fields per se. And it provides a bit more flexibility in how you can think of data governance in relational databases, as you might be enforcing them using uniqueness constructs or using primary key, foreign key relationships. The third feature we talk about is a dynamic lookup. A dynamic lookup, essentially, you can think of it as a left outer join in terms of a relational database. But what it allows you is to blend data from multiple sources for analysis. So you can perform a left outer join to an unsharded collection in the same database in MongoDB. And you can use this as a filter to find the documents which are based on the join collection. An example could be that you could say that here's a document with all the cars, and here's a document with cars which have, or here's a collection for which cars which are specific attributes. And now we can say do a lookup, and based on the lookup, find me all the cars which only has leather seats, for instance. In this way, earlier you could do this by having a collection which has all the properties or all the attributes required you to filter. But now with dynamic lookup, you're not required to have a single collection which has to have everything you may need to operate on the data set. This is done via the MongoDB aggregation framework, which we talked about earlier. And there's a stage called lookup stage in the MongoDB aggregation framework, which allows you to implement this left outer join kind of capability to do a lookup into your collections. On top of that, MongoDB 3.2 also added few more features or few more operators per se, which allows you to better do database analytics and search. This moves the code, or this moves the complexity away from your application into the MongoDB layer. So instead of implementing all of these functionalities back into your application, you can now rely on these operators and just use these operators to have the functionality implemented based on the MongoDB server side. Now, the other part is the MongoDB connector for BI. The MongoDB connector for BI allows some of the popular BI tools to connect to MongoDB and allows you to take data from MongoDB and represent them as tables or relations back for your BI, so you can quickly visualize or analyze the data set sitting in MongoDB. The MongoDB driver, which is provided, or the MongoDB connector, basically what it does, it translates the SQL query issued by these BI tools into MongoDB equivalent queries, which are then executed or sent to MongoDB for processing. Then it takes the result set back from MongoDB and converts that result set back into a relational structure or tabular format, so these tools can use that to allow you to intersect or to allow you to analyze that data set per se. Finally, there's a new GUI tool available for MongoDB, which is called MongoDB Compass. The MongoDB Compass, as you can see in the screen, allows you to connect to a database and visualize your schema of the database. You can see things like what are the frequency of the fields, for example, what are the frequency of the types of a particular type in the database. You can also use that to determine validation rules you might impose using the MongoDB new schema validation. It allows you to view documents. Not only that, it allows you to build queries in a graphic manner in a sort of drag and drop way. And it does allow for you to integrate authentication also with MongoDB, which means that it supports the MongoDB's current authentication mechanisms, whichever you choose in terms of deploying your MongoDB server. And it can allow to say that who can access the table or who cannot access these collections back in MongoDB. This is not the list of full features which are available as part of MongoDB 3.2 release, but this just gives you an idea of what are the things which were released with MongoDB 3.2 recently, so you can plan your deployment accordingly. So now that we have a basic idea of what a MongoDB is in terms of it being a NoSQL dynamic schema-based database, and what are the new features which are part of the latest release, we're going to talk about how do you run MongoDB in a highly available and a scalable way. The first thing what we're going to talk about is MongoDB replica sets. So as of all of the things we have been talking about today, we were assuming that the MongoDB is a single node database running. If you need to scale out that database, the first thing is considering replica sets. The replica sets is basically a high availability construct with MongoDB. So it can ensure your MongoDB is available during many types of failures. Failures such as network partitioning, failures such as single node failure. Not only that, the MongoDB uses a fast failover replication algorithms to provide you such stringent SLAs. The MongoDB 3.2 has a new version of a protocol which allows you to enforce a failover in a much more stringent way or in a much faster way. You can use replica sets to do things like disaster recovery, to do things like maintenance, and multiple other ways. The way it works is you add a new node of MongoDB in a group called replica set. These new nodes become something called secondaries. Every operation you do in terms of write, they go only to the primary, and primary creates a log of those operations which are called op log, and that op log is shipped asynchronously back to all the secondaries which are part of the replica set. And these secondaries, when they get the op log, they replay the op log to get back to the same state of a primary, and which is the arrows here in there which says the replication, and the replication is primarily happening by something called op log. Whenever a primary fails for any reason within a replica set, all the secondaries basically go under an election to say that which will become a new primary. And when the new primary happens, when the election of new primary happens, one of the secondaries become a new primary, and all the rights are now issued to the new primary. If the old primary comes back online, it knows that a new primary has been elected, and it will start acting as a secondary for the replica set. So based on that, one of the patterns, for example, you could do is your application could be talking to a primary which is only using the newly released in-memory storage engine, but it has two other secondaries which are using the WireTiger storage engine. The primary is not writing any data to the disks or to the drives, but the secondaries which are using the WireTiger are persisting the data to the drives. So in case if your primary crashes, you still don't lose any data. Not only that, you could use a secondary in a way that it's a lower priority, and you can connect that to your analytical applications, such as any of the BI tools mentioned above or before. So you don't put extra load on your primary in terms of reading data from that replica set. And these allows you to create multiple patterns in terms of deploying MongoDB in a much more effective way for a high availability construct, but not only for also doing load isolations, for also doing things such as backups and recoveries, because you could attach a hidden member which is part of the replica set, and you can use that hidden member to always take your backups without ever interrupting your entire replica set or the current workloads which are happening against your replica set. This is a construct for doing high availability primarily, but other construct for doing scalability in terms of adding more capacity on how applications can write more data back to your cluster is called sharding. It's a scale-out horizontal scale-out design for databases, in which basically what happens, you distribute a data set in set of specific ranges. And these ranges basically distribute a data set across multiple nodes. It is a common best practice to have each shard be a replica set itself. And MongoDB here can automatically balance the data across the shards as your data grows or as you're writing new data set into the system. MongoDB supports 3 types of sharding. The first is called a range-based sharding. In the range-based, you're basically saying that you are distributing the data based on the ranges of the keys. Range being, for example, let's say 1 to 100, 100 to 200, 200 to 300, and such. Hash-based sharding, in which you're uniformly distributing the data based on MD5 hash of the shard key. Let's say shard key be a user ID, and you're saying that I'm using the hash key of the user ID to distribute my data among the shards. The tag-aware sharding is basically you're providing a mapping of a shard keys to a tag to say that data with such keys are only going to the given shard. You can use this construct to implement things such as let's say that whenever a document or shard key has a country as US, you want to send that to only a shard which resides in US. So that way you can do a geographical deployment patterns. You can also do things like optimized storage or tiered storage to say that my current data goes to a shard which is designed for high concurrency or high reads and write, but my older data are going to shards which are designed to do reads and write faster in a much slower manner as compared to the primary shard. Each shard can be a replica set, and each shard can use a different version of the MongoDB API. Not only that, they can also use a different storage mechanism and a total different configuration. A shard does not mean that you have to kind of add complexity to your application. All of the data sets, all of the code or all of the application logic related to sharding is handled by MongoDB itself. The way it works is by using something called query router. The query routers basically take the query from your application or driver, and they, based on that queries, determine which shard the query should go to. In certain cases, it could happen the queries which are not using a shard key, then the query writer will basically aggregate all the data back to all the shards, and then take the data back from all these shards and then aggregate it on their side. For example, if you have a range-based shard key and you issue a query from your application, then the query router will check that which key or which range does the given shard key falls into, and will accordingly send the query back to shard 1, 2, or 3. So these are two basic patterns in terms of deploying MongoDB on a scalable and highly available way. And again, to recap, the first we talked about is something called replica sets, in which case you are adding more nodes to a MongoDB to provide you high availability. In second case, it's something called shard, in which case you're adding more capacity to your MongoDB deployments to help you with capturing more data, processing more data. Sharding is a good way in case you're limited by your RAM, by storage IO, or even by your data processing capabilities. If you're limited by any of these hardware underlying infrastructure requirements or underlying infrastructure capabilities, then you can add more shards to get a scale out capabilities. These are very specific to MongoDB, but now what we're going to talk about is how do we take these deployments and translate them into our AWS architectures. So the first thing which comes is, what are the instance types? So as you might know, the AWS EC2 infrastructure, AWS EC2 service provides you ability to deploy instances on AWS Cloud. There are various types of instances in AWS Cloud. For example, the general purpose, which starts with M notation, M3 and M4 class of instances, compute optimized, which are C3 and C4 class of instances, memory optimized, which are R class of instances, and storage optimized, I class of instances, which provide you locally attached SSDs, and D class of instances, which provide you a very high storage based on magnetic disks. In general, whenever you're starting with a MongoDB workload, it's a good idea to start with M optimized or M class of instances and attach EBS volumes to them. Amazon EBS volumes are volumes which you can create separate for instances and attach them to your instances and use them as block drives. So we would recommend that you always start with the M class of instances and attach a volume called EBS GP2, which are SSDs based instances for everyday use with MongoDB. In case you realize as your deployment grows further, you realize that you are bottlenecked by the compute or by the data processing capabilities, it would be a good idea to move to a C class of instances, and the WireTiger storage APIs or storage engine helps you with concurrency control, which allows you to write or which allows you to use the underlying CPU in a much better way as compared to the previous generation of memory mapped storage engine. The entire premise of MongoDB is about serving data out of the memory. It uses these underlying storage engines to load data either into the VIA Tiger cache or as memory map files. So in case you are seeing high latencies in terms of accessing your data in MongoDB, then the next advice would be to move to our class of instances, which provide you much higher memory on the EC2 instances. You could also use the new in-memory engines on a primary or a secondary to kind of serve data much faster, or load larger working set. A working set is defined as the data which MongoDB needs to serve all your queries. So the larger the working set, the better you can optimize it based on the memory optimized instances in AWS EC2. All these three instances, all these three classes, you're going to use Amazon EBS Volumes in particular GP2. But as you move to the storage optimized instances, these instances comes with local instance stores, which are SSDs or magnetic drives, SSDs in I class and magnetic in D2s, to create very optimized workloads using the instance stores attached in there. The one thing you have to be careful when using I2s and D2s with the local instance stores are that whenever these instance stores are, or whenever these instances are terminated or stopped, all the data on that is lost. But with EBS, even if you terminate or stop an instance, the data still persists on EBS, which can allow you to create some more very unique deployment patterns on AWS. But if you're using an I2s and D2s to get very high performance workloads based on local instance stores, we would always recommend that you use at least a three-way replication for each replica set to ensure that you don't lose a single, if you lose a single node, that you don't lose your data sets for there. The link below gives you very specific recommendations on how to choose Amazon EC2 instances based on certain workloads, which we have summarized here. So as I mentioned earlier, if you're using a general purpose or compute or a memory optimized instances, it's always a good idea to attach Amazon EBS volumes because they persist beyond the lifecycle of the instance. If you want to start with MongoDB deployments, using a GP2 volume is a good performance for general workloads. But if you need that SLA-driven performance, then we would advise that you look into EBS PIOps volumes, which gives you the consistent performance. EBS GP2 volumes, the performance is relative to the size of the volumes, but in EBS PIOps, irrespective of the size of the volumes, you can ask for a given kind of performance from those volumes. So if your data is very small, but you still need a very high performance, then you could consider EBS PIOps for that kind of deployment. If you're using EBS volumes with a EC2 instance, always use EBS optimized flags or EBS optimized feature. EBS optimized feature with the EC2 instances gives you additional bandwidth to your underlying EBS storage, and which helps you with making sure that you're not competing with your bandwidth for both EBS and replication per se. So if you use a EBS optimized instances, your replication can happen on a separate network plane. But if you use EBS, that will happen on a separate network or separate network plane, and that will not intersect or that will not conflict with each other. You could also use EBS snapshots for backup and recovery, and we will talk about that in a bit further down the line. EBS snapshot allows you to implement basically backups and recovery using a single API. By using a single API, you can create an entire backup, and whenever you create a new node, you can attach a new volume created from that backup, which we call as snapshots. That's a consideration in terms of deploying for a single node of MongoDB. But if you look at Amazon Global Footprint of the infrastructure, we have presence in geographical regions, which are outlined as circles, and they are called as AWS regions. You can think of a region as a location in the world where we have presence. For example, in Northern Virginia, in Oregon, in Northern California in US. And within each region, we have separate zones, which we call it availability zones. And each availability zone is basically, you can think of as a cluster of data centers, which provide you very high interconnect between these data centers. The circles here represent each region. The bluish circles represent the regions which are to be launched soon, and the numbers within the circle tells you each availability zones for that region. You can use these AWS Global Footprint to deploy some very unique architectures with MongoDB on AWS. Let's take a look at how. The first thing, we talked about MongoDB replica sets, using replica sets for high availability. So in this example, we are saying that we are deploying a highly available MongoDB cluster within a single region. Within a single region, we are using 3 availability zones. And this aligns with the best practices recommended by MongoDB that you should at least use 3 distinct data centers for high availability. One of the AZ has a MongoDB cluster which is running a primary. And then there are 2 other AZs with each MongoDB secondaries which are acting as a replica set in total. And this pattern, even if your single AZ for some reason is not accessible, your secondaries can become primaries or even can provide you with a complete failover in such a situation. Building on that, now once you're gone from a single replica set deployment to a sharded deployment, in this case you are distributing a data set into multiple partitions, and you can repeat the same pattern, but here what you're doing is you're changing the AZs in which the primaries are running. So instead of running the primary in the single AZ, which you could run, both the primaries for shard A and B in the single AZ, you are putting them into distinct AZs. This gives you not only high availability, but scalability within a single region of AWS. Each of the AZs, as I mentioned, are supported by a high-speed interconnect, which gives you very fast access to data replication between the MongoDB primaries and secondaries. A lot of AWS services, for example, Kinesis itself, whenever you write to Kinesis, it writes data to 3 AZ on a minimum, but yet gives you a millisecond responses in terms of writing data or back to Kinesis. So the cost of connecting data between AZ in terms of network latency is very, very low, and which allows you to still keep your deployment very highly available across AWS. Now we are going to go from in a region to across regions, and we would recommend that you can consider this mostly from a disaster recovery scenario. In case an entire region of the world gets wiped out, the probability of that happening is quite low, but for some network failure, let's say, or some network partitioning that happens, in that case, you can run your deployment across regions. When you do a deployment across regions, you have to be careful in the sense of what's the read and write's going to happen across regions. Because as opposed to the interconnect between AZs, the data across regions are flowing over a public internet. And we would highly advise you that either you look into a VPN interconnect between your regions on AWS, or you consider MongoDB SSL feature, which is part of MongoDB Enterprise Advanced, to make sure that your data in transit is encrypted. And further, the latencies in across region deployments could be very high, and that's something you would need to monitor by using a metric called replication lag in MongoDB. We will talk about that monitoring as we go along further down the slides. So coming back to a disaster recovery pattern, one of the principal thing you want to do is you want to run a MongoDB secondary in another region with a lower priority. Running a lower priority ensures that whenever a primary fails, the disaster recovery pattern running in that second region or the secondary in the second region does not become a primary ever. So your applications are still reading and writing from primary, but it allows you to kind of rebuild your cluster in case something happens to one region. So you can run the secondary with lower priorities, which means that they will never become a primary in case of any failure in region 1. So you have high availability based on the earlier pattern of running multiple copies of the same data set in region 1, but you're still doing a replication across regions. in region 2 to ensure that in case anything happens to region 1, you still have all the data available. You can deploy the same pattern in terms of doing a sharded cluster instead of just a replica set. And as you can note that secondaries are running with lower priorities in region 1. You can see for both shard A and shard B, on the left-hand side in the first quadrant, you can see secondary lower priority, which is for shard B. And on the right-hand side, on the upper right, you can see a shard A, which is secondary for lower priorities. So basically what you've done is you have copied the same structure of a replica set and multiplied that or copied that across multiple shards to deploy a disaster recovery pattern across regions on AWS. But combined with these patterns, what it allows you to do is basically scale your infrastructure in a very global way, or scale your MongoDB deployments in a very global way. For instance, you can deploy, your deployment could be global, but yet your applications can access the data locally. For instance, that a user could read or write to your application from anywhere in the world, but if he's back in hometown, he could actually use the nearest, closest location to read data from that. You could do this using something called a read, a read preference, where a read preference can say that read data from the closest member based on the ping distance. So what MongoDB will do is basically when you try to read it, it will ping all the servers, and whichever comes the closest in terms of the ping being done, it will read data from the data set. And you can also use this pattern to do a replication across the world so that you have a copy of data available across the world to read from that. So in this case, you have a primary sitting in one center of the world, but as the user travels from the primary, he has access to the data at any part of the world based on the locations you have replicated onto. So these are some of the patterns you can do once you are beyond the highly available and scalable scenarios to really do a very global deployment scale across AWS using the regions and availability zones. So there are a lot of things we talked about in terms of how to deploy MongoDB, replica sets, what are things we should consider, what are the things we should not consider. But all of these are best practices you need to consider when you're deploying MongoDB. The question really becomes that how do we really ensure that my deployment is basically adhering to these best practices? So MongoDB has two artifacts called Ops Manager and Cloud Manager, which allows you to leverage and implement these best practices without really reverting to custom scripting or deployment tools per se. Both the Ops Manager and Deployment Manager basically take the best practices of things we talked about, of things what MongoDB engineers have learned over the years, and they package them as one solution which you can use to deploy your MongoDB in a very efficient way, right? What it gives you, not only that, it gives you a way to deploy very quickly, but yet be able to deploy in a very repetitive way. They also have other toolings in terms of you can use MongoDB Visual Query Profiler, which is part of Ops Manager and Cloud Manager, to see what is happening within your MongoDB database. It has point-in-time backups and also optimizations in terms of rolling out indexes or suggesting indexes for your database. What are we going to do is we're going to talk about all of these features in the next slides. And in case you don't want to use Ops Manager or Cloud Manager, we also will discuss some of the manual things you could do to get to the same level of DevOps kind of way to deploy MongoDB on a cloud. Ops Manager is something which you will run on your own, but Cloud Manager is the same service, but in a hosted way. So you don't need to worry about running Ops Manager on your own, but you can just use Cloud Manager to do the same things exactly. So the first thing is how they really work. If you remember, earlier we talked about one thing, which is that when you run a MongoDB server, you run a MongoDB instance. So in Ops Manager or Cloud Manager, the primary way you interface with them is by deploying a MongoDB agent, which is running with your MongoDB server. And this agent can communicate to Ops Manager or Cloud Manager by sending them information as it happens securely. If you use a Cloud Manager can not only automate the provisioning of the instances on the cloud providers like AWS, but it also installs the ops manager, it also installs the agents on those instances. So you can use them to kind of deploy the data set or deploy a MongoDB cluster, whether be it a replica sets, whether be it a sharded cluster, or any sort of goal you want to get to. The primary way that you work is you go to Ops Manager or Cloud Manager and set a goal. These agents talks to the Ops Manager or Cloud Manager, get a goal, and then they do actions on those goals on the local running instances. The goal could be like building an index. The goal could be like updating a deployment or even doing a deployment such as a replica or sharded clusters in AWS to give you very high availability or scalability. Now, in case you are trying to deploy MongoDB and you don't have access to Ops Manager or Cloud Manager since they're part of MongoDB Enterprise Advanced, we have also built a quick start. Rick, who is here answering some of our Q&As during this webinar, had worked with us to build this quick start. This quick start basically gives you a pattern or gives you a very quick way to deploy MongoDB in a production way on AWS. You can deploy things such as within AWS VPC. You can think of VPC as a confined area of AWS in which your instances are running and can be only accessed by you over the network by using security groups, which are something like firewalls. You can even use the quick start to deploy replica sets, shards, config servers, and customize the kind of storage you want to use in terms of EBS. The link here is aws.amazon.com/quickstarts, and you can quickly get to deploy a MongoDB on AWS in this way. The primary difference that Quick Start is just a way to deploy MongoDB in case versus a Cloud Manager or Ops Manager, which provides you other features, which we are going to talk about now. So the first thing is monitoring and alerting. So Ops Manager monitors over 100 metrics and provides you simple charts or graphs based on those metrics so you can understand how your database is behaving. It tracks the key performance indicators across dozens of optimized charts, which you're seeing some examples on the screen. But not only that, you can create custom alerts based on these metrics. So when the metric is out of range, you can have the alert delivered to them via SMS, HipChat, PagerDuty, and much more other endpoints per se. And these alerts allow you to be the first to respond in there. MongoDB Ops Manager or Cloud Manager also provide you RESTful APIs in which you can consume these metrics and integrate with other APM platforms like New Relic, and we'll take a look at that further down. But if you want to do it yourself, in case you want to implement the same set of features, you have to use the multiple set of tools across MongoDBs. For example, MongoSet and MongoStat, sorry. You can run database commands such as server status, database status, collection status. You can use tools such as Ganglia, mtop, Munin, Nagios, which allows you to monitor. You can use these metrics created by either running these commands, either running these tools, and collect those metrics and send them to things, for example, let's say into AWS CloudWatch, or even trigger a notification using Amazon SNS, for example, so it can deliver your notifications to your emails, phones, or any other endpoint. Not only that, you could use these metrics to do things like auto-scaling. So you can say that whenever my read latency whenever my database is 80% full, I want to shard my database, for example. And you can implement that using auto-scaling triggers, for example. The backup and point-in-time recovery, which is provided by Ops Manager and Cloud Manager both. And the way it works is basically similar to what we talked about using op logs. So with Ops Manager and Cloud Manager, whenever you do a change to a database in terms of writing or updating a value, the op log gets shipped securely to the Cloud Manager or Ops Manager. And using the Ops Manager, using the op log, the Cloud Manager and Ops Manager can provide you a way to restore your data set with a point-in-time recovery. This is the only feature which provides you a cluster-wide snapshot of sharded clusters in a single fashion, in a single interface per se. But not only that, you could restore to you can restore to point in time, and you can even restore collections or databases per se instead of restoring the whole cluster based on whatever your impact might be in case of a failure. The Cloud Manager separately supports a two-factor authentication, so to ensure that only the people who have access to that can restore that. If you're using a manual backup process with Amazon EBS Volumes, then as you mentioned that you should definitely consider using a hidden member within the replica set for backups. You should consider using EBS snapshots, which is a feature to take a backup of your EBS volumes. If you're using EBS snapshots, definitely consider journaling with your MongoDB. Journaling is a way, whenever you do an operation, the operation before happening or before getting committed gets returned to a write-ahead log. And the write-ahead log, in case of failure, allows you to get your database back to a consistent state. If you're using the WireTiger engine, the WireTiger engine by default has checkpoints to ensure consistency, but still we would advise you that you use journaling if you're using EBS snapshots for your backups. You could also use db.fsync lock, which basically flushes the data in memory back to drives, and then you can take a backup of your volumes and then do a db.fsync unlock to get your database back to operating. Whenever you do fsync lock, it basically locks your database so no more writes can happen. The reads can still happen. And again, as the link mentioned here, gives you more detailed recommendations or more specific recommendation on how to take backups in these cases. So finally, the Visual Query Profiler, which basically not only allows you to see the queries as a way of time, what's the latencies for the queries, how fast they're running, it actually suggests indexes back to improve your query performance and automates the rolling index builds. In the sense of rolling index builds, what it really means is that a best practices wise, it is that you first roll out an index on a secondary and you gradually move the indexes back to a primary. So you do on secondaries and then do on primaries. It might take a whole lot of effort to automate that, but with Ops Manager or Cloud Manager, this is a single click again operation where not only you are seeing what is happening with your queries, but you can use the indexes suggestion and also roll out the indexes as required. If you're using a manual way to do it, what happens really with a MongoDB is that every time you run a query, it has a database profiler which stores these output of the database into something called system.profile, which is basically a cap collection. And you can use that cap collection, you can access that cap collection that is system.profile using MongoDB drivers or APIs and figure out how what query is taking how long, why it is taking that long, and get to those metrics to help you basically diagnose what is going wrong with those queries. These are some of the resources which you can access in terms of deploying MongoDB on AWS. The first one being a white paper, which allows you to see what MongoDB best practices are. The second one are production notes, and these production notes are very handy in terms of they tell you what are the file system you should use, for example. For instance, it will tell you that you should not use ext3 Linux file system for your MongoDB because of the way how allocation works in ext3. It gives very specific recommendation in terms of how much, how should you adjust your U limits, the read ahead settings, and other things with MongoDB. I think I lost something. All right, cool. So that was it, and I hope you learned something out of the best practices webinar for MongoDB on AWS.